Okay, calculus, 13.8, and even 13.9, because it's just word problem applications of 13.8, is my 100% favorite section in all of Cal 3. It's extrema of functions of two variables. So if you recall, extrema in Cal 1 is where you like to find like the maximum and minimum of a function, only now we're dealing with two variables here, so there's a little more going on. So let's talk about the extreme value theorem, as like a recall from life. If f is a continuous function of two variables defined on a closed bounded region R, there's at least one point in R at which f takes on a minimum and one that takes on a maximum. So this is really just an extension to two variables. Recall the definition of extrema. The function has a relative minimum if all the values around that point, x and y, so in this case the z value, is larger and everywhere around that point. It has a relative maximum if all values near that point are lower. So if we talk about neighborhoods, that may not mean as much to you as higher or lower, but they normally, if you ever get to real analysis, if you're doing math, you will deal with delta epsilon neighborhoods, and I'll save that pleasure for you when you get there. So in three-dimensional terms, to have a relative maximum or a relative minimum, you kind of need to be at the top of a hill to have a maximum, or you need to be inside a crater to have a minimum. To locate relative extrema of f, you can investigate the point at which the gradient is 0. Now, since the gradient is made up of the individual partial derivatives, that means all partial derivatives must be equal to 0 for the independent variables for the point to even be considered a partial maximum or minimum, or relative maximum or minimum. So here's that in more clear terms. Definition of a critical point. F to be defined on an open region. The point is a critical point if one of the following are true. Partial derivative for x and y are both 0, or one of them does not exist. If f is differentiable anywhere, option 2 isn't possible, so it's only that both of them are equal to 0. So relative extrema can only occur at critical points, just like in Cal 1 where you would find all the critical points and you would test them to see if they were a maximum, a minimum, or neither using the sign test. Same thing, we're going to test points. Okay. Yes, I would say theorem 13.6 is kind of obvious, but that's okay. Determine the relative extrema of the function f of xy equals 2x squared plus y squared plus 8x minus 6y plus 20. So we need the partial derivatives to both be equal to 0, so we need to find the partial derivatives. The partial derivative of x is 4x plus 8. The partial derivative of y is 2y minus 6. I set them equal to 0. 4x plus 8 equals 0. The 8 moves over and becomes a negative 8 divided by 4. So x is negative 2. Add the 6 over to the other side and subtract 2. It looks like y is 3. So that means negative 2, 3 is a potential relative extrema because the points have to go together. Now, if you look down here, there's a picture of this thing. It looks like it's a cone that's upward facing, and there's only one point with negative 2, 3. That's negative 2, 3, 3 in this case, and it actually is a minimum. But we can find it from this critical value. And technically the point has an x, y, and z value, but that's the x and y value, and you can plug them in to find the z value. Now this could have been achieved by simply completing the square for both variables x and y, because the factored form of this equation is 2 times x plus 2 squared plus y minus 3 squared plus 3. What would that have given us? What makes this inside 0? Negative 2. What makes this inside 0? 3. And then that 3 would just be the z value that goes with it. So realistically, this point is not really negative 2, 3. It's negative 2, 3, and then you plug back in to get the z value that goes with it, which in this case is 3. Okay, so what? Now, it's nice to have maximums, it's nice to have minimums. But in the past, we were only testing one variable, And so that is not as problematic as it's going to be testing two variables. What if we have like a maximum in terms of y and a minimum in terms of x? So we have this new thing called a saddle point. When the two functions don't agree on what happens, it is possible that if you look at the shape of a horse saddle, look, it looks like a minimum from the left and right direction. But if you look at this direction, the x direction, it looks like a maximum, and they meet kind of in the middle. This is called a saddle point. It's neither a relative max nor a relative min because the two variables essentially cannot agree on whether it's a max or min. It's a max in one direction and a minimum in the other, meaning it's technically neither. But it is an interesting point. So at the point 0, 0, both partial derivatives of our negative 2x and 2y are 0, in this case, of the function y squared minus x squared. However, if you take an area around that point, there are some points that are higher than it and some points that are lower, which means it's not a max or a min. Now, how can we check for relative extrema? In general, how do we check even for maximums or minimums? We can check these things using the second partial derivatives instead of having to graph every time. So our second partial derivatives, which in the past, we would use the second derivative test, the concavity, to generally determine if it was concave up, it had to be a minimum. If it was concave down at a point, it had to be a maximum. Now we've got more complicated things going on. So let f have continuous second partial derivatives on an open region containing a point a, b, for which the x partial derivative and y partial derivative are 0. To test for relative extrema of f, consider the quantity d. D is the second partial derivative with respect to x, so take the derivative with respect to x twice, times the second partial derivative with respect to y, minus the partial derivative with respect to x and y. So we take it derivative with respect to each variable once and square it. If d is greater than 0 and the f of xx is greater than 0, then f is a relative minimum at a, b. If d is greater than 0 and f of xx is less than 0, then f is a relative maximum at a, b. If that d is less than 0, period, it's saddle point, and the test is inconclusive if that d value is 0. And we'll actually use the second partials test when we do all of the problems in the next video, or at least one of them.